Okay, the recording started. Good morning and welcome to CSS321. This is week 12 lecture. And in today's lecture, we will still continue our journey about the Turing machine. Okay, but this time we will look at the variation of the Turing machine. Okay, because so far we have been looking at the definition of the Turing machine as a deterministic machine, okay, and also a machine that has exactly one tape, one infinite tape as a memory. Okay, but this time we will look at another variation of Turing machine, like the one that have multiple tapes, and the one that is non-deterministic. Okay, and then we will show later that um, despite all these extra features that we are adding to the Turing machine, it doesn't make the difference to the expression power of the machine at all. Okay, which means that at the end of the day, all this variation of the Turing machines can be converted to the deterministic Turing machine that we have seen before. Okay, and and then at the end of this lecture, we will look at another grammar, okay, which will be the one that describe the recursively enumerable language. Okay, and that basically we will conclude the the Turing machine topic and also this course. Okay, but before we get into the content, okay, there is a announcement that I need to make first. Okay, so the first one is about the final exam. Okay, so I posted on the Google Classroom already, but here I just want to clarify and remind it that it is there. Okay, so what is the information that you need to know about the final exam? Okay, so the final exam will be on the 3rd of December, and it will be between 9 a.m. to 12 p.m. Okay, so the questions, the exam will the exam consists of 5 sections, where each section will have 20 marks each. Okay, and these 5 topics will be corresponding to this. Okay, so the first 4 sections will corresponding to the topic in set theory, regular language and finite automata, context-free grammar and push-down automata, and the Turing machines. Okay, so the first 4 sections will be the multiple choice questions, while the last section will be the open questions where you have to type your answer and describe or explain whatever the questions say. Okay, and the topic in the open questions may come from any of the topics that we have learned. Okay, so it may say that it is a tentative instruction, but it's pretty much doesn't change anymore. So you can think of this. This will be the final version already. Okay, and what else? Okay, so for the final exam, the protocol is pretty much the same as the midterm, I believe. Okay, so basically you will be divided into groups, and each group will have a proctor. Okay, so and this will be announced later. Okay, we don't have the list yet. Okay, but it will be posted later. Okay, and then later on, each proctor will create a Google Meet link and then send it to you, and or basically post it here, and then at the time of the exam, you just join the corresponding group. Okay, just join the group that you are assigned to. Don't go to different group. Okay. Uh, okay, what else? And then, okay, so you need to be join the Google Meet by 8:45. Okay, before the exam time, 15 minutes before the exam time at least. And you need to use your SIT account. Okay, don't just use your personal one. Don't do it. Okay, and okay, so basically, why do you need to be there like 15 minutes earlier? Okay, so during the 15 minutes before the exam, the proctor will check your student ID and authenticate you basically. Okay, so he will check your camera and everything that you are following the protocol that they are there. Okay, so be there early. Okay, 15 minutes before the exam, so the proctor can do his job. Okay, and then you need to turn on your camera and must always be visible. Okay, you cannot just stand up and walk away and then come back and continue the exam. Okay, you should be able to I mean the proctor should be able to see you all the time during the exam. And then what else? And then during the exam, you're required to turn off your microphone and switch on the speaker. Okay. Don't use the headset or earphones. Okay. And only turn on your microphone when the lecturer or proctor asks you or need to communicate with you. Okay. Or if you need to or if you have an urgent request or something, okay, then turn on your microphone. Okay. During the exam, please dress properly. Okay. Since it will be recorded. Okay. So just dress properly. Okay. It doesn't have to be the uniform. It doesn't specify that. Okay. Just dress properly for the exam. Okay. Not like being naked and something like that. Okay. What else? If you have a technical difficulty during the exam, your camera go down, you lose the internet connection or something like that, please log back into the Google Meet as soon as possible. Um, okay, and then continue your exam. Okay, don't just leave it like broken like that, unless it is like cannot be fixed. Okay, what else? What else you need to know? Okay, if you need a bathroom break, okay, you need to let the proctor know, and then only one person can have a bathroom break at a time. Okay, so what else? Okay, you must stay invisible, Google Meet the entire exam time. Wait, did I say that? I think I I thought I said that already. Oh wait, no, I'm not. Okay. Um, what else? Okay, so you need to stay visible in the Google Meet during the whole exam time. Okay, you shouldn't miss from the screen, shouldn't walk away. Um, okay, so please, if something went wrong, okay, please make it like work back as soon as possible. Okay. What else? And then okay, so the exam questions will be provided in Google Form, like just like in the midterm. Okay, so you can just do it on Google Form, and it will be closed at 12:05. Okay, so there's like a 5 minutes grace period that if you have difficulty with submitting your work, okay, you have 5 minutes grace period only. Okay, so please don't submit later than that. Otherwise, um, it won't count. Okay, so what else? The exam is open book. Okay, so you basically can use extra device like PC, calculator. You can have textbook, your lecture notes, your papers, whatever prepared. That's fine. It's open book. Okay, but you must do it alone. Okay, you complete your exam alone. Okay, do not share it with another or discuss with another. Um, okay, everyone else is forbidden. Okay, do not share it or discuss it with anybody. Okay, because it's forbidden. Okay, so you shouldn't discuss it to other students, either from your course, from other course, from anywhere, including any person that is around you at the time of the exam as well. Don't do that. Okay, basically don't talk to anyone. Okay, what else? And that's it. Okay. Um, I think that is pretty much the standard exam protocol for SIT, isn't it? Okay, so basically it's pretty much like the midterm. Okay, so there should be no problems, right? So is there any questions about the exam? Okay, if you are all good, then let's go back to our content then. Okay, so before move on, okay, just another quick announcement. Okay, so today we will have the last quiz and also the problem set. Okay, and the deadline for the quiz will be 12 p.m. today, and while for the problem set, the deadline will be the Thursday of December 2nd. Okay, so it will be the day before the exam. Okay, so and I think that's it. Okay, so that is all the announcement I have. Okay, so if there are no questions, then no questions, right? Or is there any questions? Okay, if there are no questions, then let's go to our content in today lecture then. Okay, so basically, the topic that we will cover today basically are two main parts. The first part will talk about the different extension, the different variations of the Turing machines that we can do. Okay, so mainly we would look at two variations, which include um, adding extra tapes to the Turing machines. Okay, and the second one would be make the Turing machine non-deterministic. Okay, so that is the two main variation that we will look at today. And then at the end, we will look at the another grammar, which is called the unrestricted grammar. And this grammar can describe the can describe the recursively enumerable language. Okay, and uh, and that's pretty much it. Okay, so after we do that, then basically we define, I mean, as you can see so far, we will define like a pair all this time. Okay, like we will pair up the machine and a language. Okay, where the language can be described by some kind of grammar or symbols. Okay, like for example, regular expression is describing the regular language. The context-free language is described by the context-free grammar. And for this one, the the recursively enumerable language is described by the unrestricted grammar. Okay, however, we don't have the grammar for the recursively grammar. The recursively language. Okay, so what else? Okay, yeah, that is the what we will cover today. Okay, so let's get started. Okay, so first, extensions of Turing machines. Okay, so for the Turing machines, okay, we will consider the effect of extending the Turing machine models in mainly two directions. Okay, so first one, we will introduce multiple tapes instead of one. And the second one is to introduce the non-deterministic deterministism. Okay. Okay, so what else? Okay, but at the end of the day, after we introduce all these variations, you will see that at the end of the day, all these Turing machines have the same power in the sense of the expression power or the language that they can describe basically. Okay, so at the end of the day, you can see that they recognize the same class of languages. Okay, and we will prove that by showing that you can build an equivalent original Turing machine, the deterministic Turing machine that is equivalent to all these variations. Okay, so that is how we would do it. Okay, so what else? Okay, oh, I guess let's start then. Okay, so let's start with the first variation, which is the multi-tape Turing machine. Okay, so we define it this way. A multi-tape Turing machine is just like the Turing machine that we've seen in the previous lecture, which let's call it a deterministic Turing machine. Okay, but this time it will have several tapes instead of one. Okay, and then to be more precise, we will call it a K-tape Turing machine, which means it is a Turing machine that contains contain K infinite tapes. Okay, and okay, so that is what we mean by the multi-tape Turing machine. Okay, and we can specify the number of tapes specifically by using the this word K-tape Turing machine. Okay, so now let's look at the capability of this kind of machine. So for this kind of the machine, with the extra tapes, what you can do is this. Okay, so for each tape, the machine can scan by read or write at every head. Okay, where this time, when we have multiple tapes, it means that we also have the multiple head as well. Okay, so with multiple heads, it means that this multi-tape Turing machine can read and write on all tapes at once in one step. Okay, so that is what is described here. Okay, so the multi-tape Turing machine, uh, what it can do in one step is that it can read all the symbols from all its tape. Okay, so it can read the symbols from all its tape. Okay, but it can read only one symbol from each tape where the head is located. Okay, so it can only read one symbol where the head is located on each tape. Okay, and then what else? And then at the same time, it can write exactly one symbol, or at most one symbol, back into every tape as well. Okay, and it can write only the location where the head is. Okay, so basically you can think of it this way that for the multi-tape Turing machine, you basically just have the multiple tape and also the multiple head that you can exploit. Okay, so what make it a little more complicated is only this part, I believe, is that, in my opinion, is that right now when you have multiple symbols from these multiple tapes, when you update the current state, you also need to take into account all these symbols from every tape as well in order to um, transition to another state, to the next state. Okay, so that's how it works. Oh, okay, so for the writing to each head, you can either write or move it as well. Okay, so and this can be independent to every tape. Okay, so you can write the different symbols to each tape, or you can move this tape and then the next one you write something down. Okay, any combination is fine. Okay, so that is pretty much basically what is the multi-tape Turing machine. Okay, so now let's look at the picture a little bit to describe it. So as you can see here, okay, with the conventional Turing machine that we've seen earlier in the previous lecture, we would have only this finite control, a tape head, and then one tape. That's it. I mean, is all we have in the conventional Turing machine. Okay, but with the multi-tape Turing machine, now you have multiple tape and you also have multiple head. Okay, and when this machine read the symbols from the tape, it must read from all the tapes. Okay, it must read from all the tapes. And when you write and then you need to write something back to the tape as well. Okay, either write something or move the head. Okay, and you can do it. I mean, each tape you can do different things to another. Okay, it doesn't have to be the same operation to all tapes. Okay, it can be different operations. For example, in tab 1, you might write a symbol back. Okay, in the tab 2, you might move the head to the left. In tab K, you move the head to the right. That's fine. Okay, and that is what you can do with the multi-tape Turing machine. Okay, so that is basically the intuitive idea of the multi-tape Turing machine. And now let's look at the formal definition of it. Okay, so let's see. So the K-tape Turing machine is defined as the 5-tuple, just like the conventional Turing machine. Okay, but the only main difference is the transition function, that this time it must take into account that it has multiple tapes, or to be precise, multiple symbols that are read from multiple tapes. Okay, so here we assume that we have K tape, so that is why it is sigma to the power of K. And this is like all the possible combinations of the symbols that you may read from all the tapes. Okay, while here, okay, so here basically just a transition function of the, um, okay, oh, okay, I think I missed the symbol somewhere here. Okay, it basically should be the, okay, here just there should be like an equal sign there. Okay, or you can think of it, just remove it then. Okay, just ignore that. Okay, okay, so basically, for the input, you need what? The input, you need the current state, which must not be a halting state. Okay, that's why this k minus h. And then multiply by all the input symbol that are read from that are read from all k tapes. Okay, and then after you get this as the input, the transition function will determine what is the result. And the result would be this k. This k will be your next state. Okay, this will be your next state, and then here will be the operation that you do to each tape. Okay, so you can either write a symbol back into it at the location of the head, or you can move the head to the left or to the right. Okay, and you can do different things on all k tapes. Okay, so let's see. So here, for example, here this is what the transition function will look like for the multi-tape Turing machine. So here for each state queue, okay, and and let that we have the this k tuple is the symbols that we read from the tapes. Okay, so let it be A1 to AK, which is the symbol that we read from the tape at the current locations. Okay, and then the transition function will look like this. We give the current state and we give the current the input that we read from the tapes. Okay, and then what we get as the result would be the next state, the new state that we transition to, and also the actions that we perform on each tape as well. Okay, so that is how the multi-tape Turing machine is defined formally as the math symbols. Okay, so what else? And then with that, okay, now after we have the formal definition of the machine, now we also need to define the configuration. Okay, so that we can define what kind of configuration is accepted, which in turn will be used to determine what kind of languages or string, which string is accepted, and then finally we can define the language accepted by the machine. Okay, so that's why we need to define the configuration. Okay, so how do we do that? Okay, so normally for the configuration of the conventional Turing machine, we need to have what? We need to have the current state and also the tape content and also the head, the location of the head. Three things. Okay, so that fact is still the same. Okay, but this time we just have multiple copies, or not multiple copies, but multiple values of the tape content and also the location of the head. or the location of the tape head. Okay, so let's see. Okay, so here we define M as a K tape Turing machine, then the configuration would look something like this. Okay, so here you would have the current state K, and then next what you have is, okay, so this will be the here we will use the convention where we have the left side of the tape and also the tape content and the right side of the tape content. Okay, we will divide the tape content into two parts, divide at the location of the tape head. Okay, so this one will be the left hand side contents of all tapes. Okay. Oh, sorry. This will be the left hand side content. Okay, this one will be left hand side content, and this part will be the right hand side content. And then we make it like K times for K tapes. Okay, as you can notice, okay, so for the left-hand side symbols, left-hand side content, okay, you may have, you can put any alphabet in it, including the blank cell as well. Okay, but for the right-hand side, okay, for the right-hand side content, it cannot end with a blank. Okay, it can only contain the alphabet, and the last symbol must not be a blank. Otherwise, we will have the problem where we can describe like one configuration. There will be multiple ways to define the same configuration then, and we don't want that. And another option is if there is no content on the right hand side, or to be precise, there are only blank cells on the right hand side. We put the empty string in the right hand side content, and that's pretty much it. Okay, and that is how we define the configuration of the K-tape Turing machine. Okay, so that's it. And that is pretty much and that is pretty much all we have about the multi-tap Turing machine. Okay, so I think so far we defined everything we need. We defined the machine, we defined the configurations. Now we are able to use it now. Okay, so here for this example, let's look at how can we use this multi-tape Turing machine. Okay, so here we will use it in for the task of copying machine. Okay, so here is the idea. Here's the idea of the copying machine. Okay, so okay, so the idea is like this. Okay, we basically remove the oops, what happened? Give me a second. What's wrong with you? Oh, okay. Duh. Okay. Okay. Um. hmm. Okay, give me a second. My computer is doing something weird. Oh, okay. Okay, never mind. Okay, sorry about that. Okay, so what is the idea? Okay, the idea when we have the two tapes, what we will do is this. First, we will move the head on both tapes to the right, okay, while we copying each symbol on the first tape onto the second tape. Okay, so this is how it works. Okay, when we are, mm, okay, is do I lacking or something? Can everyone hear me fine? What's going on here? Yeah, isn't it? Okay, give me a second. Oh, okay, you can hear me, right? Okay, okay. Okay, so what happens? Okay, so here for the two-tape Turing machine, what happened is, okay, so first step, we will move both heads to the right. Okay, and while we move heads to the right, we will copy the content from the first tape to the second one. So here's how it works. So at the beginning, the input will be copied to the first tape only. Okay, so the input will be in the first tape. and that's it. Okay, other tapes will not have the input. Okay, so that is why we need to perform the first step to copy the content from the first tape into the second tape in order to copy the input. Okay, and what else? Okay, and then we will use blank as a symbol to tell us that it is the end of the input. Okay, and that is why what it say here. Just keep copying until you find a blank. Okay, then what else? Next, the second step is then we just rebase the head of the second tape to the left. Okay, so basically we just put the head of the second tape back to the original position. Okay, and then we will just start to copying the content from the second tape back into the first one. Okay, so that way we would be able to copy the same content into into the same tape. Okay, so we just keep basically just keep copying the input back into the first tape. Okay, right, um, and then we just halt when we hit a blank. Okay, so think of it this way, that the second tape act like a clipboard. Okay, so basically when you say copy, you copy the content into the clipboard first, and then when you want to paste, you copy the content from the clipboard back into the location where you want to paste it. And that is how it works basically with the two tape. So okay, so as you can see here, it is make much more sense. I mean, it is very easy to follow when you have multi-tape. How do you say that? When you have the multi-tape uh, Turing machines. Okay, despite the fact that we have seen the uh, a conventional Turing machine version of the copying machine already. Okay, let me find it quickly and show you. Okay, so where is it? The Okay, there it is. Okay, let me show you quickly. Okay, maybe I shouldn't do that. What happened? Okay, give my computer time to process. Okay, so here is what it looks like. Actually, maybe it's better to I just copy it. Oops, that. Okay, okay, okay. Give me a second. Okay. Da, da, da. So okay, so what I want to make a quick comment about this. What's going on? Okay, so here's the idea. So let maybe I should draw it to make it easier to understand. Oops. Okay, my bad. Okay, so what's going on? Okay, so this is what happened with the two tape. Right. Okay, so first we have blank, and then we have some like the input is there, blank. Okay, something like this. Okay, so for the two tapes Turing machine, what happened is at the beginning, so you have this, and the second one just have like a blank everywhere. Okay, so this first tape and this second tape. Okay, so as it say earlier, what happened is first it just read and copy the content um, from the first tape to the second one. So okay, so this is what happened. Okay, and then second step, move it back to the original place for the second tape, and then copy the second tape back to the first one. Okay, so you just keep copying, and then you get something like this. Okay, so as I say here, okay, so uh, the second tape acts like a clipboard. This is what happened here. Okay, and it looked very easy to understand what happened. Okay, but on the other hand, with the conventional Turing machine, okay, we are able to build the copying machine, this copying machine as well. But look at how it works. Okay, so as you can may see here, it will have something like, let's say, it have something like this. Okay, so what it did is that it has to what does it mean? It has to like copy one symbol at a time, as you can notice here. Okay, it need to read like the first symbol, and then when it see the first symbol, um, when it see the first symbol, it has to like move all the way to this location, write the first symbol down, okay, and then come back here to copy the second one, and then go back to write the second one, come back to get the third symbol, and then come back to write the third symbol, and so on. Okay, so you need to go back and forth in order to copy the whole string. Okay, and that, I mean, and as you can see here, it looks like a multiple of non unnecessary steps. Okay, and it is very difficult to for humans to follow what is going on as well. Okay, so um, okay, so as you can notice here, I mean, it is easier to just have like a two tape Turing machine to do this. Okay, so now let's look at the okay, so here a quick example. Basically what I just described earlier, isn't it? Okay, so here just to show you how does the copying machine C is performed when we designed it as a two-tape Turing machine. Okay, so as I say, first we at the beginning the input only exists in the first tape. We copy it to the second tape, and then we move the head of the second tape back to the beginning in order to prepare for pasting it back into the original the first tape, and then we do it, and that's it. So the result will be in the first tape. Okay, the other tapes are not considered here. Okay, the result of the first tape is returned back to the machine. Okay, so if you write it down as a symbol, so here we will use the basic machine symbols as before in order to simplify our machine. Okay, otherwise it will have a very large diagram, as you can imagine. Okay, so how does it work here? Okay, so what happens here is that here we will abuse the notation a little bit. Okay, so this time when you see the superscript, it doesn't mean that we do this machine multiple times. Okay, but it means that which tape are we performing this operation on? Okay, for example, here r to the power of 1 comma 2, it means that we perform right shift to both tapes. Okay, so first at the beginning, we move both tapes to the right by one position in order to move away from the blank symbol. And then here, when we have this age and then this condition like this, it means that check the first tape that the symbol is not blank. Okay, and if the symbol is not blank, what you do is you write that symbol into the second tape. This is what it means. A to the power of 2, it means that write symbol A in second tape. And then you repeat the process. Okay, so as long as the content in the first tape is not a blank, you keep writing it into the second tape, and that is exactly what we want, isn't it? And we keep doing that until we find a blank in the first tape, and that is basically the end of the input. And then what else? And then after that, we rebase the head of the second tape. Okay, move it back to the left, and that is why we use the left blank on the second tape. And then again, both of the tapes move to the right and keep writing So this time we check on the second tape that is not a blank, and we keep writing the content from the second tape into the first tape. Okay, and keep doing that until it finish, and then if we hit a blank, then we just move to the halt state. Okay, you can think of it that that is basically there's a halt state somewhere here that we let's say something like and then we just halt. Okay, something like this. Okay, if we see a blank, halt it, and basically we just accept that that string. Okay, and that's it. Okay, so that is how we can implement the copy machine with the two-tape Turing machine. And as you can see, it is much easier to understand compared to the previous one. Okay, so here this exercise tells you to design a two-tape machine that decide this language. Okay, so basically this machine are pretty much the same as the previous one. Okay, the only difference would be this part. Okay, that you would check for symbol Z, a symbol C instead of blank, and that's pretty much it. Okay, and basically you change all this condition as well, isn't it? That you want as long as you don't oh maybe not the maybe not this one. Okay, so okay, so what else? Okay, so as long as you don't see the letter C, okay, that is fine, because here they want you to build a machine that basically um, create a copy of the string, okay, and separate it by a symbol C. Okay, so basically you can build it just like what you see here. Just change a few symbols, and then you're good to go. Okay, so that is the two tapes machine. What else? Okay, okay, so here we would look at the theorem. Okay, that tells us what is. Okay, so here. Hmm, okay, here we will come to the theorem that tells us that with a K-tape Turing machine, there is a standard Turing machine that is equivalent to it. Okay, so here we assume that we have the K-tape Turing machine. Okay, so and for the sake that to make this K-tape Turing machine different from the standard Turing machine, we specify that the number of tape must be greater than 1. Okay, if the number of tape is equal to 1, then it is basically the standard Turing machine. Okay, so here, we say that let's say we have a multi-tape Turing machine M and also a standard Turing machine M prime. And what else? Okay, so basically these two machines share the same alphabet. What else? And that's it. And what else? Okay, and then let's say that we have okay, so then what we can do is this. Okay, the standard Turing machine that we built, it will basically accept the same language as the machine M. Okay, and we define it by this. So we say that machine M on input X halts, okay, with output. Okay, so we say that. So here we're talking about when it accept the string, right? Okay, so when this machine M given the input X, it halts. If it halts and the output Y will be on the first tape, okay, then what we can do is this. We can build an equivalent standard Turing machine that will halt on the input X as well. Okay, and it will be in the same halting state and also the same output Y on its tape. Okay, so this is the theorem say this, that we can do that. Okay, so from this definition, basically we can conclude that every multi-tape Turing machine has an equivalent single-tape Turing machine. Okay, so um, as you see before, by extending the Turing machine with multiple tapes, okay, at a glance, when you look at it at a glance, it may seem that you are given like the increase the power of the machine to be able to describe a more complex language. But it turns out that we can actually build a Turing machine that accepts the same language, but that Turing machine might be very complex and very difficult to build compared to the multi-tape version of it. Okay, so but anyway, we will show that every multi-tape Turing machine, we can build an equivalent single-tape Turing machine. Okay, and if we can do that, then we just finish the proof that every multi-tape Turing machine has an equivalent single-tape Turing machine, and that is what we will do. Okay, so the idea is this: we will build a, a standard Turing machine that represent the that is equivalent to the k-tapes 1. Okay, and the idea is this: first, hmm, um, okay, so the first idea that you need to know, okay, in order to prove this is this: that we can actually store the content on multiple tapes into one tape. Okay, so and what you can, how can we do that? What you can do is this. Okay, and okay, so what you need to do is this: you need to create new symbols. Okay, so in this case, the first new symbol that you need to create is the this pound sign. Okay, or just this symbol. Just call, okay. Let's just call it this symbol. Okay, so we create this new symbol, and we will use it um, as a like a symbol that tells us that this is the end of the tape. Okay, so this symbol will separate different tapes. So for example, here we have 3 tapes. Then we will just copy these 3 tapes onto the same into the single tape, while we put this sharp symbol to separate the content between tapes. Okay, so for example, here you see for the first one, 01010, that is the content of the first tape, and then you put the sharp sign, and then followed by AAA, which is the content of the second tape, another sharp sign, and then BA, and then sharp sign. Okay, so yes, you can represent multiple tapes using a single tape, but it will make it is much more, make your life much more complex. Okay, but here, just for the sake of proof, it is possible. Okay, and another new symbol that you need to do is that you need to also track the location of the head as well. And we will do that by uh, creating the new symbol. Okay, so basically for every alphabet, we will create a new symbol that is the alphabet with the dot above. And this symbol will help us indicate where the location of the head is. Okay, so here, for example, here we have what? We have like 4 symbols, right? We have like 4 alphabets: 0, 1, A, and B. Then the alphabet for the new standard Turing machine will have like another 4 symbols with the dot above. Okay, so here we are adding a lot of new symbols to the machine, and that is how we do to represent the K tapes with one tape. Okay, so now with this idea, then we can assume that even we have multiple tabs, we can just simulate it with just one. Okay. Um, and then okay. So here, just to give you the more ideas about how can we process, or I mean, or update this multi-tape using this representation. Okay, so what you need to do is to simulate a single move on the multi-tape Turing machine. There will be a lot of steps. Okay, not just multiple move, but it will be a lot of move on the standard Turing machine that we built. Okay, So what does it has to do? The standard Turing machine M prime has to scan its tape through all the sharp sign in order to basically go through all the tapes one by one. And then for each tape, it has to um, it has to update according to the operation that we perform on each tape. Okay. And another cautions that you need to be careful. Another point that you need to be careful is when you add some symbols to the content in the tape. Then what happened is all the tabs behind it has to shift to the right in order to make a new blank space for you to add the new symbol into the tape. Okay, so you need to do that as well. Okay, if you are adding new symbols or writing symbol into a blank space, basically. And okay, so yeah, okay, so basically you just follow what the transition or the um, you just follow the operations that the machine M tells you to do. Okay, so what else? Dun, dun, dun. Oh, okay, this is what they're talking about when you need to do the right shift if you trying to add new symbols to it. Okay, otherwise it's fine. You don't need to do. You just need to read the content on each tab content. Okay, so here so far, okay, so with that idea so far, oh, oh, okay, and what else? Okay, so with uh, hmm, give me a second. Okay, so the hmm. Oh, okay, never mind. Okay, so that is pretty much the idea. Okay, so with that, then we can simulate the K tips with just one tape. Okay, and that is pretty much conclude the our proof idea. Okay, so here's just a proof idea. Okay, so if you want to see the details of the proof, you can look at it in a textbook. Okay, that will provide you the more details. Okay, but here is the main idea of the proof already. Okay, so all is left is that you just give like a formal math definitions and so on in order to make it a valid, proper valid proof. Okay. Okay, so with that theorem, then it leads to this corollary that a language is Turing recognizable or semi-decided by the Turing machine if and only if some multi-tape Turing machine recognize it. Okay, so I mean this is just from the previous from this theorem. Okay, that I mean, this one already kind of state that already that it if the machine halts on input X is also the standard Turing machine empire also halts on it as well, and if not, then it may loop forever or reject it. Okay, and that is also apply here as well. Okay, so that is pretty much the definition of this recognizable. Okay, so and actually, since I mean, as you can see here, since you are able to basically build a equivalent Turing machine to the multi-tape Turing machine, so this corollary also applies to the Turing decidable machine and also the functions that the Turing computes as well. Okay, so it means that if there is a multi-tape Turing machine that decides some language, then you can find there is some Turing machine that is also decided as well. And the same goes for the function that if this multi-tape Turing machine computes some functions, then you can build an equivalent Turing machine that compute the same function. Okay. Hmm. Okay, so that is pretty much it about the multi-tape Turing machine. Okay, so we introduce the what the definition is, give you the definition, give you the intuitive, and also give you the proof that it is equivalent to the standard version. Okay, so here there's also another variation of the of the Turing machine that you all should know as well. It is the multi-head this time. This time it is the multi-heads. Okay, so different from the multi-tapes in the sense that this time you still have only a single tape, but you have several heads. Okay, so um, so it is a Turing machine that has only one tape, but you have several heads on it. Okay, so it means that when you compute, okay, the transition, you can read multiple symbols from the tapes from each location of the heads, and then at the same time, after you make the transition, you can do some operations on these heads, either write a symbol back into it or move the location of the heads. Okay, and what else? Okay, so for this one, there's two things that you need to be careful when you use this kind of Turing machine. The first one is that they may be the situation where multiple heads are at the same location at the same time. Okay, when you read it, that's fine, but when you write it, okay, if you try to write different symbols to the same location, then we have the problems. Okay, so normally, how it works is this. Okay, normally we will assign a priority to the heads. Okay, so the heads with higher priority will be performed first. Okay, and then if it is writing at the same location, then the first one who write at that location will be kept. Okay, and other symbols that are trying to write at that location will be ignored. Okay, another situation that you need to be aware is that it may arise when head is at the leftmost cell. Okay, and it's um, okay, and then the transition function just keep instructing it to move to the left. Okay, so it's kind of got into the loop where the head is keep getting the same operation of going to the left where it hit the leftmost cell already. Okay, we can call it a hanging. Okay, because it's just kind of like stuck there. Okay, so this is another situation that you need to be aware when you use the multiple heads Turing machine. Okay, so just another variation, and as you can see, I mean, it basically used the same proof as the multiple tapes, okay, that you can build an equivalent Turing machine with just one tape and one head. Okay, and basically it just following, extending this idea, okay, and that's pretty much it. Okay, and that's it for the and that is it for the first variation of the Turing machine, which is the multi-tape Turing machine. Okay, is there any questions? Okay, if there are no questions, then let's move on to the non-deterministic Turing machines. Okay, so this is the second variation of the Turing machine that we will look at. Okay, so this time, so far we're looking at the deterministic Turing machine, which means that every step we have a transition function which will give us only one possible solution of one possible outcome for each step, right? At every step, there is only one possible outcome all these times, no matter what. Okay, even if it has multiple tapes, even if it has only one tapes, even if it has multiple heads and so on. Any variations so far that we see, it is deterministic. Okay, so there's only one outcome at each step. all the way to the all the way to the end. Okay, but this time we want to look at the non-deterministic Turing machine that and just like the non-deterministic finite automata, it means that at any step there may be multiple outcomes of the machines. Okay, so it means that there are several possibility that you can proceed at each step. Okay, so okay, so such the non-deterministic Turing machine, okay, might have like a combination of the states, okay, and it can use like a combination of scan symbol and more than one possible choice of outcomes that you may choose. Okay, so it's just like the finite automata, but this time you can just, you can read basically the outcome can be different, okay, with the same input symbol that you read and at the same state, it may write different symbols, it may perform different operations, and it may transition to different next state. Okay, there might be multiple choice, multiple possibilities. Okay, so that is basically what is the non-deterministic Turing machine. Okay, and what else? Okay, so next, let's define the mathematic definition of it then. So the mathematic definition of the non-deterministic Turing machine is this. The non-deterministic Turing machine is this machine M, and it is a quintuple. Okay, so it has the 5 component as the same as always. Okay, just like the conventional Turing machine. Okay, and also these 4 symbols are also the same. K, sigma, S, and H are also the same. Okay, the only difference is the transition function, and which is now the transition relation. Okay, because it's no longer a function. Okay, if it is a function, it must have only one possible outcome. But this we allow several possible outcomes. So that is why it is just a transition relation. Okay, and what else? Okay, and as you can see here, okay, we defined it as a transition relation, and this part looks just like the transition function. Okay, the only difference is that now we allow that with this the same given input, it may produce different outputs. Okay, but for function, if there's only one input, okay, if each input has a unique outcome. Okay, but for the relation, we don't have that restriction anymore. Okay, so the transition can begin with from any state that is not a halting state, and the input that we read from the input tape, and then after the transition, we get the new state and also the operation that we perform on the tape at the location of the head, which is either write a symbol there or move the tape ahead to the left or right. Okay, and then what else? Okay, so this is the mathematic definition of the non-deterministic Turing machine. Okay, which is very similar to the non-deterministic finite automata. Okay, so here, just to give you the recap on the relation of the configuration. Okay, so before that, when we look at the standard Turing machine, okay, when we look at the standard Turing machine, we say that one configuration yield another, and it can be only one of these cases. Okay, where the first case, you basically just write a symbol to the location of the head. The second case is you move the location of the head to the left. And the third case is when you move the location of the head to the right. Okay, and 2A and 2B are just the sub cases that may occur when you find a blank at the end of the string. Okay, and the same goes for 3A and B. Okay, but this time, however, when you have the transition relation, now this time this relation or configuration yield is not restricted to a single value now. Okay, this time one configuration may yield several other configurations in one step. Okay, so this is the main difference between the deterministic Turing machine and the non-deterministic Turing machine. So this time a configuration can yield multiple configurations. Okay, so here we need to, and because the computation is different, now we need to redefine the accepting and the decide and semi-decide and explore accepting and rejecting states. Okay, so here we define like this. We say that M is a non-deterministic Turing machine, and then we say this. We say that this non-deterministic Turing machine M accepts a string W, okay, if this string, okay, given as the input, okay, inscribed in the tape, and also start at the initial state, we can compute it and eventually get to the halting state at some point. Okay, and here we just want only one possibility to get to the halting state. Okay, it doesn't matter that most of the possibility may end up um, with a loop or rejecting a non-halting state. That's fine as long as there is at least one that can get to the halting state. Then we accept it. Okay, and then what else? Okay, and then for the semi-decide, we say this. Okay, since we okay, for the semi-decide language, okay, we say that machine M semi-decide the language L if for every string in the language, the machine M halts on the input, halts on every string in the language. Okay, and when we say halts here, it just means that the machine M can get to the halting state given that input. Okay, exists a computation that lead the machine M to the halting state with the given input. Okay, so it doesn't matter that most of the possibility might lead to the forever loop or others. Okay, but as long as there is one existing computation that lead to the halting state, then you are fine. It will consider as accepting the string. Okay, so that is how the non-deterministic Turing machine works. Okay, so just as long as you can find one possibility of the computation, then you're good. Okay, what else? Here we will look at the non-deterministic Turing machine. Okay, but this time we define the decide. Okay, so previous slide we look at the semi-decide. Now we want to define the decidability. Okay, so here let M be a non-deterministic Turing machine. We say that machine M decide this language. Okay, if the following conditions hold. Okay, so it means that okay, so the okay, so basically, what happens is and, give me a second. Uh, oh, okay. So okay, so the idea is this. Okay, look at the second one first. Okay, the idea is this. If the non-deterministic Turing machine M decide the language, it means that for every, basically for every string in that language, that machine must, if you give that string as the input to the machine, it must lead to the accepting state. Okay, a halting state y, which is the accepting state at the end. Okay, and on the other hand, if it doesn't decide the, if it reject the string. Okay, this time instead of leading to the halting state of rejecting one, or usually we use the symbol n for the rejecting state, right? This time we don't need that. For the non-deterministic Turing machine, we don't need that. All we need is that if it cannot get to the, I mean, if the machine M cannot get to the accepting state within n steps, then we can conclude that the machine reject that string. Okay, and therefore the language is not. Uh, um, it means that the machine doesn't decide the language. Okay, so here we will use this instead, and we will see it later why. Okay, because just to give you a quick idea here, that since non-deterministic Turing machine can have like a multiple branch of ways to perform things, and that means that it may like never it can like loop forever for some branch, and for some possibility it might just go to nowhere and so on. Okay, by having these numbers, it's like, think of it like this, as think of it like you are using like a recursive function. Okay, normally in your computers it will have like a failsafe that if you try to use recursive function and keep doing recursive function more than like a number of times, then it just gives you error where it says something like the memory, the heap if a heap memory is run out, something like that, that it can no longer uh, uh, recursive itself any longer, something like that. So the same idea here, that um, since the non-deterministic Turing machine, it just can have many impossibilities. Okay, so it can many of them may lead forever. It just many what I mean is many possibilities may lead to a loop forever. Okay, and that is why we need this number n to like a limit that, and then so that we don't need to check. We still need to check all the possibility, right? Since how could you know then that it rejected? Okay, so and so that is why we need to set this number so that we can limit the number of space that we need to check. Okay, otherwise we need to check forever, and then we won't be able to decide it, and then it will be a semi-decide instead. Okay, so that is why for the decide we need to set this limit, so we have like a finite space that we need to check, and then so we can always decide either to accept it or reject it. Okay, and that is why we need this first condition here. Okay, what else? And then for the compute, okay, it just basically a like a modification of the previous one, since decidability and the computation is pretty much the same thing, isn't it? To be able to compute, you need a recursive language first. Okay, and that is why the definition here is pretty much the same. Okay, and for the computation, it's say like this. Okay, let M be a non-deterministic Turing machine, and we say that M computes a function f, okay, if the following conditions hold for every string that the machine M can compute. Okay, so look at the second one. It means that it must be able to compute it and lead to the halt state, and then at the end, the content in the tab will be the output. Okay, while the first condition is the same as previously, that it the this string will lead to rejection. Okay, and this machine doesn't compute this function. Okay, so and that is pretty much the definition of the non-deterministic Turing machine. Okay, so actually, I think this is a good time to take a break. Okay, so right now it's 10:20. We will continue at 10:35. Okay, so at this point, okay, we have looked at the definition of non-deterministic Turing machine, and then after the break, we will look at the proof that we can build an equivalent deterministic Turing machine that is equivalent to the non-deterministic one. Okay, so let's take a break. We will continue at 10:35. Okay, let's take like a around 15 minutes break. Okay. Okay, so are you ready to continue? Okay, let's continue then. Okay, so what did we talk about in the first part of the lecture? Okay, so far we have been looking at the different variations of the Turing machine. Okay, so the first variation that we look at is the multi-tape Turing machine. Okay, so and then we give the intuition of what can it I mean the extra features, what can it do, and also the formal definitions, and also the proof that we can build an equivalent standard Turing machine to the multi-tape one. Okay, so we can do that, and which means um, the the multi-tape Turing machine is equivalent in terms of the expression power as the Turing machine. Okay, so there's no difference in terms of the expression power or the language that they can describe, decide, semi-decide, and um, you get the idea. Okay, so now and then before the break, we start looking at the second variation, which is the non-deterministic Turing machine. Okay, we give the definition already, and this time we are going to prove that we can build an equivalent Turing machine uh, to the non-deterministic one as well. Okay, so here is the theorem. It said that if there is a non-deterministic Turing machine that semi-decide or decide a language or even compute a function, then there is a standard Turing machine that also semi-decide or decide the same language or compute the same function. Okay, so basically this theorem just tell you this, that for every non-deterministic Turing machine, there is an equivalent deterministic Turing machine one. Okay, that you can build, and then they will just basically decide the same language, semi-decide the same language, or compute the same function. Okay, so how can we do this? How can we prove this? Okay, so the idea of how can we prove this? The idea is this. We need the proof idea is this. We will see the computation of the non-deterministic Turing machine as a tree. Okay, think of tree as like a tree where each node is a configurations, and there is edges connecting the possible, I mean, the possible view of one configuration in one step. Okay, so that way we will start from the initial configuration, and then from there we can like keep expanding to multiple possibilities, right? We can write it as a tree. Okay, and then what else? And then s- the okay, and then let's see from the view of the non-deterministic Turing machine first. Okay, so after we build this tree. Okay, so what we expect is this. At some point, one of the leaf node in this tree must be a halting state. Okay, and if that is the case, then we found the solution. We found we found the possible computation. Okay, that and just it just tells us that basically that the non-deterministic Turing machine just accept that string. Okay, as long as we just see one of them, and that is fine. Okay, so what else? And then think of it this way: that when we have a tree, okay, when we look at this problem as a tree, it means that we can also apply any we can apply the algorithm that we know for graph to solve this problem as well. Okay, so what happened in this case? In this case, we can look at this problem as the search problem in algorithm. Okay, when we have this tree of configurations, then what our goal is to find a node with the halting state. That is all we need. We need to find a node with a halting state. If we find it, then we know that this string is accepted by the Turing machine. Okay, so with that, we can look at this problem as the search problem over the tree data structure. Okay, and then what do we do? So basically, what you do, okay, you just build the what you have to do is just you just need to build a deterministic Turing machine that perform that graph search on this uh, non-deterministic Turing machine computations. Okay, and here we will use the breadth first search. Okay, we will use the breadth first search to do this. Okay, and the idea is that we would build a deterministic Turing machine that perform the breadth first search on the non-deterministic computation, and if the D find the accept state on this branch or on any of these nodes, then we accept it, and if not, we just terminate the simulations. Okay, and also we know the depth already. Okay, from this definition, it also gives us the depth of how far we need to explore already. Okay, so we okay it so for the decide one, then we have this number to limit our search space. Okay, so we can guarantee that it will always terminate. Okay, but on the other hand, for the semi decide language, we don't have such constraint, so it is possible to just keep looping forever. Okay, and that is the reason why we need to perform the breadth first search rather than the depth first search. Okay, use the BFS rather than DFS. Because if you use the DFS, you might get stuck in one branch that stuck in the loop forever, and then you will never have a chance to explore other um, other branch of computations. Okay, and that is why we need to use the breadth first search. Okay, so now let's move on to see how can we use the breadth first search to, using the Turing machine to perform the breadth first search in order to determine whether the non-deterministic computation will accept the string or the input or not. Okay, so we will call that a non-deterministic computation tree. Okay, so where the node is the configuration and the edges just connect between the configuration that can be used in one step. Okay, so how does it work? Okay, so that is the idea. Okay, so now let's move on to look at the details of how can we implement the breadth first search using the Turing machine. Okay, so if we can do that, then we can just perform the search on the non-deterministic computation tree, and then we just finish the proof. Okay, that we can build the same, the deterministic Turing machine that basically perform the same computation. Okay, and okay, so hmm, so let's move on to how can we show that. Let's see how can we implement the breadth first search using a standard Turing machine. Or actually, to be precise, we will use the multi-tape Turing machine to build to build or implement the breadth first search. Okay, so in this case, we will use the three-tape Turing machine to implement this. Okay, and which we show already that it can be built uh, as a standard Turing machine. Okay, so if we can build the equivalent multi-tape Turing machine, then it is the same as building a standard Turing machine. Okay, so let's see how can we build implement the breadth first search using the multi-tape Turing machine. In this case, we need three tapes. Okay, and what are these three tapes do? Okay, so the first tape is the input tape. Okay, that is not doing anything much. Okay, we just keep the input there in case we need to read it again when we do performing the search. Okay, so we just keep the input tape there and don't touch it. Okay, just leave it there in this tape, and don't make any modification to it. Okay, think of it as like a read only. Okay, it is an input tape that we will just perform the read operation on it, and we will never write anything into this, because we will need to look at the input over and over again. Okay, so don't change anything to it. And then the second part, okay, the second part is where you keep the copy of the end computations on the branch. Okay, so think about breadth-first search. How does it work? Okay, so um, hmm. So the idea is this. Okay, so the idea is that okay, the idea is this. Okay, when you do let's say you have the a non-deterministic computation, right? Okay, something like this. Okay, and this is like number 1, 2, 3, 4, 5, 6. Okay, so the number I wrote here is like the order that the breadth-first search will perform the search. Okay, it will start from the root and then go to the child of the children of the roots, and then followed by the children of the roots, and so on. Okay, so one level at a time. That is what the breadth-first search do. Okay, and in order to do this, it needs like a queue. Okay, so it needs like a queue to keep track of basically two things. Okay, it need to keep track of basically two things. Okay, so it basically need to keep track of the location of the configuration in the tree. Okay, which basically is the address tape that we do that. And then the second part, the second thing that we need to keep track is the um, is the content on the tape so far at that location. Let's say we get to this point, what is the content of the tape? Okay, we need to store that as well, and that will be in the simulation tape. Okay, and that's what basically what we needed there. Okay, and okay, and that is pretty much it. Okay, so and that's it, and that is how you basically implement the breadth first search, right? I mean, when you look at this, you put number two, node number 2 and 3 into the queue. Okay, so basically you put the content of the tape, okay, and also the address of which node are you going to visit or check it next. Okay, um, you store that in there. Okay, and then just keep going. Okay, and then just perform the breadth first search using the Turing machine from there. Okay, so that is the proof idea. Okay, so I will skip details of how would you implement the Turing machine. Okay, because that would be a lot of details. You can look at that in the textbook. Okay, I will not go through it. Okay, it would be too much details, and it can take like a whole lecture to describe it. Okay, but I mean, without the details, you should get the idea now, like how could you prove it? Okay, so basically we just perform the search on here, and which essentially is the same idea of what non-deterministic computation is doing as well. Okay, it built this computation tree in order to find a possible configuration, a possible computation that will give a halting state or accepting state. Okay, and that is what we want at the ultimate goal. Okay, and that is what also happened here. Okay, so the simulation tape and the address tape basically just keep storing the node that we need to visit next. Okay, and then also the content that we have so far in each node. Okay, and that's why we can use the sharp sign to separate the different the content in different nodes. Okay, and address here we can just store like in sequence. That's fine. Okay, and that's it. Okay, and with that, if after we implement the breadth first search, it basically just give you that this deterministic Turing machine can basically compute the same thing as the non-deterministic one. Okay, and basically conclude the proof that every non-deterministic Turing machine has an equivalent deterministic one. Okay, so and that's it for the variations of the Turing machines. Okay, so do you have any questions? Okay, so far we have looked at the two main variations of the Turing machines, and we see that they both have the same expression power as the standard Turing machine. Okay, and now we will move on to the last topic of this course, and it basically gives you the idea of the grammar that this Turing machine can um, um, basically can describe or process it basically. Okay, so this grammar is called the unrestricted grammar. Okay, so here the name is like after the context-free grammar, but since it removes some restrictions, so that is why it is called the unrestricted grammars. Okay, so let's look at the difference. What does it mean? Oh, before we go there, why we need? I mean, why do we define this grammar? Okay, because in the sense of the computation, okay, we don't have the efficient algorithm to process it. Okay, which mean that this grammar only exists in basically in theory. Okay, we don't have like an algorithm to process it or be able to run it properly. Okay, so far, and the reason that we built it, okay, is because that so far we have been seeing the language generator, or basically the grammars that we can, or symbols that we can use to build the language or explain the language, like the regular expressions and context-free grammars for the regular language and the context-free language, respectively. And we see that by having this language generator, it gives us, I mean, it is very useful to have such a language generator or the formal, okay, it just gives us like a formal way to how to generate such language, okay, defined by the language generator. And also, it will match with the machines that act like a language acceptors. Okay, so that we can prove in terms of math that, I mean, think of it this way, that the language generator act like a symbol, a math symbol that tells us what kind of language, I mean, what kind of string is in the language. Okay, and then the machines come in and act like a language acceptor that be able to given the language, we can build, I mean, we can, this machine can determine whether the string is in the language or not, and so on. Okay, but so far for the Turing machine, we haven't done that. We don't have the language generator. We just kind of we define the recursive language based on the Turing machine, right? That's what we did. Okay, we just define that the language that is accepted by the Turing machine, the language that is decided by the Turing machine is the recursive language. Okay, and that is kind of like think of it like it's like a self definition or something like that. I mean, you just use the item you just define to define itself. Okay, so it doesn't really make sense, or okay, it makes sense in the sense in terms of the language, but it doesn't give us the idea about what kind of this the capability of this language basically. Okay, it doesn't tell us the capability of the language like what we did with the regular expression or the context-free grammar. Okay, and that is why so in this last topic, we will look at we will introduce you a new kind of the language generator that is as you will see later, is the generalization of the context-free grammar, and it is um, also the class of the recursively enumerable language. Okay. So as I said before, we don't have the language generator for the recursive language. We only have the language for the language generator for the recursively enumerable one. Okay, so here let's see the main the definition, the formal definition. The unrestricted grammar is defined as the quadruple. Okay, if you remember, it is the same as the context-free grammar. We have V, we have sigma, we have R, we have S, where V is the alphabet, sigma is the terminals, and R is a set of rules, and S is the starting symbol, just like the context-free grammar. Okay, the main difference is in the rules. Okay, in the set of rules. Okay, now the set of rules is, I mean, each rule is different now. The condition on the rules are different now. Okay, for the context-free grammar, the rules are usually something like the rule is something like this, right? It's like a v multiply v star something, right? Oh no, it's not like that either. It has to be v. I cannot write. Okay, v subtract sigma multiply by v, or maybe v star. Wait, is it? Yeah, it has to be v star. Okay, there you go. Okay, so for the context-free grammar, we have something like this for the rule. Okay, but this time for the unrestricted grammar, uh, we have this instead. Okay, so what is the difference? The difference is that for the context-free grammar, we can only convert a single non-terminal symbol into a new symbols. Okay, but this time for unrestricted grammars, we can just basically convert a group either I mean we just need to convert at least one non-terminal symbols into a new symbols. Okay, the only condition is that it must contain the non-terminal. Okay, which is makes sense because for the terminals as the definition, it means that it cannot basically expand further. Okay, but this time we can use it as part of the like a part of the rule to convert into the new symbols. Okay, so what else? And that is pretty much it. That is what the unrestricted grammar is. Okay, and as you see later, by remove this restriction, then it is allow us to do many more things, and then we are able to accept or express much more languages than before. Okay, so what is it? Okay, so okay, so here V minus sigma is just basically are the non-terminal symbols that are the symbols that can be expanded further into other symbols. Okay, so okay, so here let's look at what the unrestricted grammars, the rules, what does it mean? Okay, so hmm, okay, so for the unrestricted grammars, what kind of rules are possible? Okay, so the first one is this. Okay, the first one is okay, we will define it like this, that if we can convert from this u into v, then we will just write as a pair here, where the first component tells you what must be given, and the second component tells you what will be the output or the outcome. Okay, and then what else? And then okay, so okay, so basically this just tell you how we will use the symbol to define the rules. And then the second one, okay, tell us that each rule, what happened when we apply the rule. Okay, so when we apply the rule, okay, so what do we need? Um, the, 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 hmm. Okay, so when we apply the rules, okay, let's say we have some string u, then we will get into the string the string v. Okay, if there's some rule in R, then you can just convert part of it into the new outcome according to the rule. Okay, you can just convert part of it. Okay, where w1, w2 is the part that stay the same, and u prime and v prime is the part that are modified. Okay, and of course, this transition is reflexive, transitive, and closure. So you can do it multiple times. You can do it multiple times, and that is where the language generator is defined. Okay, so it we define it like this, where this grammar G, okay, we say that a string is generated by the grammar G if that string, I mean the from the starting symbol, we can uh, perform a number of rules, and at the end, we get the string we want. Okay, and then we define that the language is generated by the grammar G if the set of all string in that language can be generated by G. Okay, so here let's look at the example. Okay, so here is an example of an unrestricted grammar of this language where it contains the sequence of letters A's, B's, and C's with equal numbers. Okay, and we see earlier that when we talk about context-free grammar, that this language is not a context-free language. Okay, but this time we will show that it can be described by can be described or generated by the unrestricted grammar. And this is one possible solution. Okay, there are multiple solutions, and this is one of them. Okay, this is only one of them only. Okay, so let's see what does how does it works. Okay, so here this is all the symbols that are possible. Okay, so basically ABC is the terminal one. The lowercase a, b, and c are the terminal one, and the rest are non-terminals. Okay, and okay, so here, what kind of rules do we have here? Okay, so the first one, we have the star symbol can be converted to ABCS. Okay, so basically this part, the first one just tells you that you can generate the equal number of A, B, and C, okay, for any times that you want. For this, the first rule. And the second rule, you use it when you have enough number of A, B, and C, then just convert S into TC. Okay, and then at the end of this, so first you apply either of these two rules, okay, and then at the end of the first step, you will end up with a string that looks something like this. You have A, B, C for a number of n times, and then n by TC. And then the second step of this language is this. Okay, I mean, you can look at this language as multiple steps. In the second step, you're just sorting out A, B, and C so that it become like this. It become A's first, and then followed by B's, and followed by C's. And then the last step, the symbol TC will be the one who lead the transformation from the uh, uppercase A, B, and C into the lowercase a, b, and c. Okay, and that will conclude uh, the grammar. Okay, and at the end we will have a series of A's followed by a series of B's followed by a series of C, which have the same number of letters. Okay, so that's pretty much it. Okay, so actually let's look at a quick sample, I guess, to give you a better idea. Give me a second. Let me copy the rules here so it's easier for us to follow what's going on. Oops, not that. Go away. Okay, so what do we do? Okay, so we start from S, right? Okay, so what else? So what do we do? Okay, so we just keep repeating these rules for 3 times. Okay, and what will we get? Okay, so use the first rule 3 times. Let me write it shorthand so it saves time, okay? Uh, to give you a better idea. Okay, so this is what happened. Okay, we applied 3 times and we got something like this, and then we apply the second rules. Okay, so the S become T. Okay, we got something like this. Okay, and what else? Okay, give me a second Hmm. Okay. What else? Um, okay. Next, for the TC, we apply what? Okay. Oh, then we apply these three rules basically to sorting out. Okay, basically we apply these three rules to sort out the ABC over here. So it become A, B, 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 C, 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 and then followed by TC. Okay, that is basically how it works. And then from there we apply this rule first. Okay, so C, as you can see here, we will convert C become, I mean TC will become after it look I mean, you basically push this symbol T to the left, and if it pass a uppercase, it will convert it into the lowercase. Okay, and this is what happened, and you repeat it for the whole time, for the whole process, and then you get something like this. Okay, and then you apply this rule to convert from BTC into TB. Okay, and then use this rule for another 2 times to convert everything into B's. And then you get TB over here. And then apply this rule from TB and A into A, something like this. And repeat this for another 2 times. And you get A, B, 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 C, C, C. Okay, and then at the end, you apply this rule, TA into the empty string to remove it, and then you're left with the string that we want. Okay, and that conclude the grammar, how you derive the string using the unrestricted grammar. Okay, and that is pretty much it about the unrestricted grammar. Okay, and what else? Okay, so here the last thing that we need to look at is this theorem that say a language generated by the unrestricted grammar, uh, then it must be a recursively enumerable language. Okay, and also um, true for both directions as well. Okay, so here's the proof idea. I just give you the proof idea. The details will be in the textbook. We will not go through the details of it. Okay, the proof idea is this. So let's say that we have this grammar G, and as we did for every time we want to show that such thing is in the language, it is the recursively enumerable language. What we do is we just build a Turing machine. Okay, we just build a Turing machine that is semi-decided, and then we just finish the proof. That's it. Okay, just like we did in the previous lecture, isn't it? When we try to prove the recursive language or recursively enumerable language, we just build the Turing machine. And the same idea applies here. We just build the Turing machine that semi-decide the language, and then we just finish the proof. So okay, so for the hmm, okay, so for that, I will not go into the details, but you should get the idea that we can read the whole, starting from the starting symbol, and then we have like a set of instructions in the Turing machines to convert it according to the rules in the unrestricted grammars and so on. Okay, and with that, and actually we can use the non-deterministic Turing machine to perform this. And because we have proof already that non-deterministic Turing machine is basically the same as the deterministic Turing machine in terms of the expression power. Okay, so we can just build the non-deterministic Turing machine to semi-decide the language generated by G, and then we are good. Okay, so that's it. Okay, and that is how we can prove that unrestricted grammar is recursively enumerable. Okay, and here you might argue that, hey, why not use the same idea to prove that it is a recursive language then? Okay, the problem is this. The problem is that since the unrestricted grammar, we can kind of, as you can notice earlier, we can kind of apply the rules forever. Okay, like for example, this first rule we can apply as many times as we want. Okay, and in the sense that when this number of A's, B, and C are not the same, let's say we have a string that they don't have the match, and we need to determine or describe it with the grammar. Then we can kind of like loop forever and keep putting a substitute s by this abcs forever, and we're stuck in the loop forever. Okay, so what I want to point out here is that we may stuck in the loop forever during the derivation of the grammar. Okay, and that is why it is also possible for the Turing machine to loop forever as well, and we don't have the guarantee that it will halt. And that is why we can only semi-decide the language at best. Okay, and that is why the theorem only apply to the recursively enumerable language and not the recursive language. Okay, so here the last part, here the exercise is that we want to find the grammar that generate the language, okay, where number of n's is equal to the power of n. Sorry, number of number of letter a's is equal to the 2 to the power of n, where n is can be any positive integer. And this is this could be one possible grammar that generates such language. Okay, and okay, just to give you a quick idea of what it can do. Okay, think of it like this: that basically this the letter M. Okay, we introduce two basically three. We have like four non-terminal symbols. Okay, and what does it do? Okay, S just act like a starting symbol. T T is there for the recursion. Okay, and M is there for the M will tell us that how many times we want to perform the power there. Okay, so if we say that we want to perform 2 to the power of n, that will be n symbols of m. Okay, and then the dollar sign just tell us that it is the end of the string. Okay, so let's see how does it work. Okay, so let's say that we want a to the power of 2 to the power of let's say 2. Okay, so we want to like 4 a's at the end. Okay, what will happen? So start from s, convert to ta dollar sign. Okay, and then for t we convert it to tm. Okay, and as I say, we will do it not 2 times. Okay, so we get tm tm m and then a dollar sign. Okay, and then from there, t will convert to empty string, remove it basically. We got with a dollar sign, and then we do this m when it's ca, convert to 2a's. Okay, this is what we get then. Okay, and then when mc dollar sign, just remove m. Okay, so we leave with dollars, MA dollar sign. And then again, when MCA, you got 2A's MA dollar sign, and then again, dollar sign, something like this. Okay, so you get, with 2 steps, you got something like this. With M dollar sign, it becomes just dollar sign, and the dollar sign can be converted to empty string to remove it, and then you end up with 4A's as wanted. Okay, and that's it. And that is how you generate the language. Okay, using the grammar. Okay, using the corresponding grammar. Okay, and and that's it. Okay, and that is and that is all we need to. That is what you need to know about the unrestricted grammar. Okay, so okay, so far, so what have okay, so that is the end of this lecture. Okay, so to summarize what we have seen so far, what happens? Okay, so as you can see at the beginning of this lecture, that we look at the multiple variations of the Turing machine. Okay, we can see that even with the additional features, we can basically at the first glance you might think that we just add the expression power to the machine, but in fact we didn't. Okay, we just make it easier for us to describe or design the Turing machine. Okay, but in terms of the computational power, it is the same. Okay, it just make it easier for us to design such machine, and that's it. Okay, and because of that, okay, it lead us to believe that maybe Turing machine is the one, is the ultimate computational model that can describe the computer, the device. Okay, so that is what we believe so far until the quantum computing comes in. Okay, and what it does is, since the quantum computing will basically have different mechanism compared to the um, to the conventional one, and also the quantum computing will allow us to solve the problems that we cannot solve with the conventional computers. Okay, and with that, it will change. It basically will change the set of problems that we can solve. Okay, because right now we define that the algorithms are defined by um, the um, basically the language that can be described by the Turing machine. Okay, but with quantum computing, it can solve the problems that even the Turing machines cannot. Okay, and that will basically break the definition that we make earlier. Okay, and that is why quantum computing creates such a hype. Okay, in terms of the theory and also in terms of application. Okay, and that is why everyone is interested in quantum computing right now. Okay, and however, the quantum computing is outside the scope of this course. Okay, but anyway, hope I hope that you learn something from this course, or more or less. Okay, for the regular language and context-free grammar, that would be the one that you will see its application in real practice more. Okay, the Turing machine is more or less theory. Okay, so you will not see much of its use in terms of practice though. Okay, so anyway, it is good to know about the Turing machine, and it gives an hope that by looking at this three types of machine and these languages, okay, it helps you expand your horizon about the problem set that the computer can solve and cannot, and give you a better idea of how a computer works. Okay, and that's it. And that conclude this course. Okay, so here's the reference, and that conclude this course. Okay, and that's it. Okay, so any questions? Oh, okay. Oops. Give me a second. There's questions asked that for the second finished diagram of example 2. Okay. Okay, so you're talking about this one, right? Give me a second. Oops. Okay, I will share the screen in a second. Okay. Okay, so you're talking about this second example, right? Okay. Okay, sure. Let's do that quickly. Okay. Okay, so okay, you can see the screen, right? Okay, so as I said before, okay, so basically this one is basically just similar to the previous to the example one. Okay, the only main difference is that we just need to change the symbol that we use to indicate the end of the string. Okay, so that is why at the beginning, oops, not like that. I need to change the pen first. Okay, so we need to do R. Um, okay, so I need to do what? R1 and 2. Okay, move to the right in order to move away from the space. Okay, and then from there, Okay, I just need to check that A1 is not equal to C. Okay, because this time, if we see a letter C, it means that it is the end of the string. Okay, and oh wait, give me a second. Decide to the machine to decide. Um, yeah, okay. Okay, so yeah. Okay, so here we need to check it, right? Okay, so we need to decide it. So basically, we just keep reading it and until we see a letter C. Okay, so oh, okay, okay, my bad here. Okay, so here it might be semi-decide or not decide. Let me change it to semi-decide. My bad. Okay, it will be semi-decide. Okay, so I will explain later why it is semi-decide. Okay, but for now, let's say that A1. Okay, so the symbol in the tab 1 is not C. What we do is that we just keep copying it to A2. That's it. Keep doing that. Okay, so basically we try to copy this part into the second tab first, and then later, okay, when we see letter C, we move on to this. Okay, so we use the else blank for the second tab so that it moved to the first. So at this point, this would be what look like on the tape. Yeah. So okay, so okay, we also need to do the uh, right shift for both of them as well, so that the position will be here on the first tab, and the second tab will be it will be at the beginning of the string. Okay, and then the first tab will be, the position will be the first position of the W as well. Okay, so we perform left blank on the second tab, and then do right shift on both tape. Okay, so that we are positioning the heads on the first letter of the string. Okay, what else? And then we just need to do the same thing that so now this time we need to compare that A1 is equal to A2. Oh, sorry, not like that. Okay, if they are, I mean, if they, or basically just check that they are the same, right? We just need to check that they are the same. Okay, if they are the same, just keep going. If they are not, we reject it. Okay, and the last case is when you have the blank. Okay, if my drawing is bad here, it might look confusing. Let me redraw it a little bit. Okay, so here let's do the loop here first. If they are equal, we just keep shifting to the right. Okay, if they're not equal, we reject it. And at the end of the day, if we reach space for both A1 equal to space and A2 equal to blank, then we accept it basically. Okay, and that's pretty much it. Okay, that is pretty much the two-tailed machine that decides such language. Okay, that should look like it. Okay, so here one more last comment. Why is it semi-decide? Is this if the language doesn't contain C? Okay, if it doesn't contain C, let's say that the language, the string that's given is like this. Okay, WW. Okay, so the machine is supposed to reject it if it decide the language. Okay, but as you can see from my definition, you can see that this can stuck in the loop forever, like over here. Okay, if it never see the letter C, it just keep going into the loop and it will never come out, and it just loop forever. Okay, and that's why it has to be semi-decide and not decide though. Okay, and mhm, maybe you can add more conditions to make sure that this doesn't happen, but for simplicity and for the explanation, simplicity of the explanation, let's leave it at semi-decide. Okay, so does that answer your questions? Okay, great. Okay, so is there any more questions? Okay, so if there are no more questions, then I will let you do the quiz, and also don't forget to do the problem set. Okay, so the deadline of the quiz is at 12 p.m. today. Okay. The Okay, so the quiz, the deadline is at 12 p.m. today, and the problem set, the deadline is Thursday, December 2nd. Okay, so don't forget to do it as well. Okay, the problem set will be available at 12 p.m. after the class.
อาจารย์คะ
Yes.
อาจารย์จะมีเฉลยพวก problem set เก่าๆไหมคะกับพวก quiz
Uh, okay, but first, please speak in English, please. I believe there are some students who are not familiar with English. Oh, sorry, with Thai language. Okay, so the question is, will I have the solution for the previous quiz and problem set, right? Um, hmm, okay, actually, hmm, uh, okay, I can do that. Okay, let me check quickly. What can I do? Um, I'm not sure that for the Google form, if I like allow you to see the solution now, will you be able to see it, or what will happen though? Okay, give me a second. The hmm. Okay, you know what? Give me a second. Okay, I may be able to give you that. Okay, but first let me um, do some backup before I make the modification. Oh, what's happening here? Okay, let me stop presenting. Okay, oops. Okay, my bad. I pressed the wrong button. Okay, okay, I will try to make it show the solution. Okay, but I'm not promising that. Okay, let me try it quickly, and then I ask you to try it and ask you that you are able to see it or not. Okay, I will try first with the quiz week 11. Let me check. What can I do? Respond. No, I'll not do that. Uh, oh, what's going on here? Okay, so the respond can see the correct answer. Um, okay, if I do that, what happened then? Okay, okay, if you could try check quiz week 11, can you see the answer now? Any of you, if possible? If yes, then I will do the same for other work that you have done, so that you can see the
yes
solution. Okay, you can see the solution now, right?
Yes.
Okay, yeah, I will do that. Okay, I will do that from I will do that later for all the quiz and problem sets, so you can use, so you can study for the exam. Okay, is there any more questions? Okay, if not, then that's it for this course. Okay, good luck with your final exam next week. Okay, and apart from that, don't forget to finish the quiz and also the problem set. Okay, so and also keep checking the Google Classroom. Okay, there will be updates about the final exam will be posted there. Okay, so um, keep checking it for any updates about the final exam. Okay, every instruction about the final exam will be given there. Okay, so please check it regularly, especially right before the exam. Okay, so please check it like more often when uh, before next Friday. Okay, so if there are no questions, then that's it. Okay, good luck with your final exam, and that's it then. Okay, bye class.